Hey, welcome back. So I want to kind of just show you so Robert Shull was emailing me, and he noted that you can always use the tabular method, and I kind of just want to show you how to do that. So you could do this instead of the U and the V thing, so you don't have to write out the U, V, and U, DU, whatever. Okay. So Robert Shull is in the full term class, Math 1620. That meets on Monday and Wednesday at 9 o'clock. So if you want to say hi to him or thanks for suggesting doing this because I like this method, you can message him in chat. Okay. So anyways, let's take a look here. Stuff like x, ln x dx. Okay. So you can use the tabular. So you do sines. And then you're differentiating, and then you're integrating. So it's always going to go plus, minus, however many you need. For differentiating, the one you pick is the u. So you use liate to figure out what goes first. So liate says log first, so ln x, and then you have x. Then you differentiate on this column, and you integrate on this column. So after you do that, you're going to immediately write down I'm going to immediately write down this term. Okay. So you'll get positive x squared ln x over 2. And then you ask yourself if you can integrate this row. Okay. I can. Okay, so my next term is going to be the integral of that. So I have a minus, so it'll be minus. There's a 1/2 constant I can pull out, and then integral x squared over x is just x dx. And then I'm done. X squared ln x over 2 minus 1/2 x squared over 2 plus c. That'll be x squared ln x over 2 minus x squared over 4 plus c. Okay, let's look at one that takes a little longer. So integral, let's say x cubed e to, let's say, the 3x dx. Okay. So again, you're doing your sine, differentiate, integrate, and you use liate to figure out which one you're differentiating. Let's get some signs going. So liate says algebraic before exponential, so you're going x cubed here, and then e to the 3x here. So go ahead and differentiate, 3x squared, e to the 3x over 3. And then you write down this guy, that factor. So this will equal positive x cubed e to the 3x over 3. And then you ask yourself if you can integrate this thing. And no, I cannot. So you'll go down to the next row. Okay, differentiating in, I get 6x. Oops, 6x. Integrating this part, e to the 3x over 9. And then you immediately write down this thing. Okay, so there's a minus. And we have 3 over 9, which should be 1 over 3, x squared e to the 3x over 3. Okay. And then I ask myself if I can integrate this row. And no, I can't. So I go down to the next row. We'll have the derivative now 6. This will be e to the 3x over 27. And immediately write down kind of the diagonal part here. So this will be plus. You get 6 over 27, so that'll be 2 all over 9. So you get plus, the wrong color, plus 2x e to the 3x all over 9. And then again, you ask yourself if you can integrate this row, and I can. Okay, so I'm going to go ahead and then I have this minus. I can factor out minus. I can factor out the 6 over 27. So again, that's just going to be 2 all over 9. And then you'll have e to the 3x over 3. I mean, we can integrate it. So e to the 3x dx. Okay, so we're ending up with x cubed. I'm going to try to smush it all in over 3 minus x squared e to the 3x over 3 plus 2x e to the 3x over 9 minus 2, it'll be ending up all over 27 e to the 3x and then plus c. Assuming I didn't do anything silly. Okay. We could always check our answers using the web. Okay, so I like Wolfram. Yeah, it's just gonna give it to me. Thank you. Come on. My computer's running slow as molasses lately. int of x cubed times e to the 3x on x. Integrate that character, and hopefully we get the answer. It's not happy about. So 9 over, so it goes x cubed, then minus, goes positive minus positive minus, so positive minus positive minus. 9 over 27 is 1/3, and then we get the x cubed, and then 9 over 27 1/3. 6 over 27 is the 2/9 with an x there, and then negative, I guess 2 over 27. Yeah. So you see, you got it. Okay. So let's try another one. Let's try one that doesn't have a bunch of work in it. So x cubed sine x dx. And so here I go with the signs, and then derivatives, integrals. Liet says we do algebraic before trig. This one looks like it's going to be another long one, huh? So I have algebraic before trig. So the next row will be 3x squared. The integral of a sine is negative cosine x. So immediately I write down, the diagonal. Right? So this will be equal to negative x cubed cosine x. I'm going to have to leave myself some room. And then I ask myself if I can integrate this, and no, I cannot. So then I go to the next row, 6x, the integral of negative cosine x is negative sine x. Immediately write down the diagonal. So that will be positive 3x squared sine x. Ask yourself if you can integrate. Can I integrate this row? Nope. So you immediately go down to the next row. So that will be 6. Integral of negative sine is positive cosine x. Write down the diagonal. So I have, in that case, plus, seems like the sign should be alternating, but there was that negative negative in there, so maybe that screws it up. So plus 6x cosine x, and then I ask myself if I can integrate this row. I guess I can. So I'll have minus 6 integral of cosine x dx, and then I can hopefully integrate that. So negative x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6 sine x, and then plus your integration constant. Okay. Again, let's go and make sure. So we have x cubed sine x. So it's 3x squared sine x. We should have one of those. 3x squared sine x is there. We'll have a negative 6 sine x, which is right there. We'll have have negative x cubed cosine x. So I have to kind of distribute it because they wrote it in a funny way. And then positive 6x cosine x. Positive 6x, yeah. Okay, so we nailed it. Let's try another one. Let's try arctan. So the trick with this is to pretend one of the functions is just a 1. So it's 1 times arctan. Liate says, so that 1 is considered algebraic. So Liate inverse trig before algebraic. So we have the arctan here, and then we have the algebraic there. So differentiating, I get 1 over 1 plus x squared. Integrating, I just get x, and I immediately write down the diagonal part. So this will equal x arctan x. And then I ask myself if I can integrate this thing. And yes, I can. This is minus the integral of x over 1 plus x squared dx. You can do a u sub. You'll have a 1 plus x squared is 2x. Divide by 2x. The x's cancel. You get a constant of 1/2. So it's going to be x arctan x. You have to show work on the test. I don't, because I've done it 20 million times. 1/2 ln absolute value 1 plus x squared plus c. Okay. As usual, we can kind of make sure that's right. Integral arctan of x. It was quicker for me to do it by hand than it was to put it in the calculator. Maybe if I wrote tan inverse, it'd be happier. There it is. X tan inverse minus 1/2 log of x squared plus 1. X tan inverse minus 1/2 ln. I don't need the absolute values, but okay, same answer. All right, let's now there's these weird ones, okay, like e to the 2x sine x dx, and that's what I was saying back here, where you're kind of you'll go down a row and then check it to see if you can I integrate, but you're also simultaneously always kind of thinking, have I seen this before? Is this the integral I started with? Okay, so that's kind of like an else statement. Did I start with this integral on this row? Did I start with using my E.E. Cummings lowercase I instead of uppercase? If you read a lot of poetry, you know what I'm talking about. So did I start with a constant multiple of this integral? Okay, so in these cases, that's kind of what's going to happen if you have an exponential and a trig function, a sine function or a cosine, e to the x sine x cosine x. Two of those kind of smushed together, you're going to have that looping effect. All right, so let's dive in here and see what happens in these cases. Sine, differentiate, integrate. Okay, so plus, minus. So Liate says trig before exponential. Okay, so differentiating at cosine x, integrating e to the 2x over 2, and then I immediately write down the diagonal. Okay, so this equals e to the 2x sine x all over 2. And then I ask myself if I can integrate this, or have I seen it before? And nope, neither one. So you go to the next row. So I have negative sine x, and then e to the 2x all over 4. Immediately write down the diagonal. And you get, so minus e to the 2x cosine x, this time all over 4. And then go down to the next row. So differentiating at negative cosine x. Oh, whoops, I didn't ask myself if I had seen that one before, or if I could integrate it. Great. Stupid freaking pen. This was circled. And then I had checked the second row. And then I circled another diagonal. And right now I'm going to check the third row. Okay. So I look at this and I say two things. Can I integrate it? No. But have I seen a constant multiple of it before? Yeah, this is negative 1/4 times the original integral. Okay. So you kind of just stop there. So I'll have negative 1/4 times the integral e to the 2x sine x dx. Right. Okay. In those cases, then it's the ones where you have to replace it with an I, right? So I'll just call the integral of e to the 2x sine x dx I. On the other side, I have all this junk. And then solve for I. And that should be your answer. So if I add that to the other side, 4/4 plus 1/4 is 5/4. On the side, at e to the 2x sine x over 2 minus e to the 2x cosine x over 4, and then plus your integration. Multiply by 4/5, and you get I is, I guess, 2e to the 2x sine x all over 5 minus e to the 2x cosine x all over 5 plus c. Right. Okay, let's see if that's what I got last time when I did this problem. What was it? 2/5 and then negative 1/5. 2/5 negative, yeah, okay. So then that would be your answer. Okay, so you could do this instead of the UV stuff. It's just, there's still a level of kind of memorization of the program, the algorithm that we're using here. But you can use this on tests now, and you don't have to worry about me saying, oh, where did you get this method from, buddy? Right? All right, so thank you to Mr. Shull for pointing this method out. You can thank him yourself in class if you have class with him. Anyways, that will do this video, and I'll see you next time.